My screen is visible. I hope it is visible to you. If it is not, please message me or ping me. Okay. So let me share my slides. Okay. Okay, fine. So good evening, everyone. So today here we are at our last class of the course, fourth week, uh, in which till now we have discussed energy harvesting, which basically means the course was basically just okay. The course was basically selection of nanomaterials for energy harvesting and storage. So till now we studied energy harvesting. Harvesting basically means generation. So generation of energy. And since you guys know, we have focused in this course on generation of energy from various sources, various renewable as well as non-renewable resources. But as you might be knowing, that generation of energy is not enough. It is if you generate a lot of energy, it needs to be used. But as you guys, as we all know, that it is not always that the amount of energy that is generated, it is not possible to use it at the same instance, or you can say that the need of energy is discrete everywhere. It mean For example, if energy is generated at a power grid station, so it needs to be distributed to the whole city, or it needs to be taken to the villages. So for that purpose, energy storage is also important. Another reason is that, for example, if you are generating energy from sun, okay, if you are generating solar energy, then it should fulfill the needs of a family or of a house or of a region for the whole timing, for the day as well as night. But at night, sun is not available. So how to use that energy generated during the day at night? So for that purpose, energy storage is also very crucial. So till now we studied the various nanoparticles which are required and which are used uh, during energy generation. But now we will be talking to in today's class, we will be talking what are the nanomaterials that are used and that can be used in storing this energy so that it can be used at a later time. Okay. So what is energy storage? Basically, it is the energy storage. It is the it is the energy which is generated to energy storage devices are the devices which stores energy which is produced at one place to use it at other place or at different timing. For example, if you are storing energy in a device at a for example at a power grid station, for example in the city power grid station, storage devices are used for storing energy, but it's energy to use that energy at different places and different time of the day. Okay. So energy storage, it is accomplished by various devices or physical media that stores energy. Storage can be done either by devices or by using different physical media. What that means, we will be discussing further. So basically, it means that energy storage does not always require a device. It can be a device also, or it can be a media also, which can assist in transferring the energy which is generated from one place to another. Okay. So it is accomplished by devices or physical media that store some form of energy to perform some useful operation at a later time. Okay. The energy storage along with renewable energy generators, PVs, that is photovoltaics, is required to increase the reliability and flexibility. Obviously, if and mainly this energy storage concept came from renewable energy sources. As you all know, that generating energy from renewable energy sources is one thing, but it should be available at all places. If we plan on making this renewable energy sources our main source of energy, since we all know that in the upcoming decades or in the upcoming century, the non-renewable energy sources may get exhausted. So when those non-renewable energy sources will get exhausted, we will be completely relying on renewable energy sources. So we need to generate electricity from renewable energy sources, but these renewable energy sources are not present at all times. So if we integrate energy storage systems along with the renewable energy storage renewable energy generators, then it increases its reliability as well as flexibility. Okay. The intermittent nature, basically the unavailable at all times nature. Intermittent, that is not available at all places and not available at all times. Intermittent means discontinuous. Okay. So the discontinuous nature of these renewable energy sources like solar energy, wind energy needs storage to deliver the right amount of power at right time as well as right quality. Okay. It is used to accommodate the projected high penetration of solar and wind energy in future grid with lower grid rejection loss. Okay. So these are some of the advantages of energy storage. Why we need to do energy storage? Okay. Now coming on to the characteristics of energy storage system. These are some of the terms which are used to characterize energy storage systems. Okay. So the first one is storage capacity, which is quantity of available energy in the storage system after charging. So storage capacity is basically, for example, if you take a glass of water and fill it completely with water, then the volume of water which is stored in it, that is basically its quantity. That is basically its capacity. So storage capacity is basically the amount of energy which can be stored in a storage energy storage device, the maximum amount of energy which can be stored in an energy storage device during during charging. Okay. Available power, expressed as an average value as well as peak value, often used to express the maximum power of charge or discharge. So basically available power is the amount of charge or amount of power a machine, an energy storage device delivers after after complete charge. Okay. Power transmission rate, time needed to extract the stored energy. So basically, power transmission rate is the total amount of time that is required for a energy storage device to extract to deliver its charge. Basically, so basically, it is the total time which is required to extract the stored energy. Okay. Efficiency, basically, it is the output upon input, that is WUT, which is the energy utilized, to ratio of WUT to WST, which is the WUT is the energy utilized and WST is the energy stored. Okay. So that is basically the amount of energy stored and here amount of energy utilized. So basically output to input. Okay. Cyclic capacity is the number of times the storage unit can release energy it was designed for after recharge, expressed as the maximum number. So basically, cyclic capacity is, as you might know, there are various energy storage devices. For example, taking battery into consideration, battery or supercapacitor into consideration. So cyclic capacity is basically of secondary batteries or rechargeable energy storage devices which can be recharged. Okay. So cyclic capacity is basically the number of times you can completely charge and discharge a machine without its failure. So for example, a battery you can use for numerous times. For example, taking mobile battery into consideration, after using your mobile for 2 years or 3 years, you might have seen that the capacity or the efficiency of your battery has decreased. Your battery takes longer time to charge and more and lesser time to discharge. So what is that? Its cyclic stability is degrading, its cyclic capacity is degrading. So what is happening? That it has almost reached its capacity of how many cycles it can charge and discharge. Okay. So basically, how many times a battery can charge as well as completely discharge without degradation of its system without degradation of the electrode material or electrolyte material or its various elements. Okay. Next is the autonomy, the maximum amount of time the system can continuously release energy. Okay. It is given by A equals to UWT by PD. UWT is the energy utilized and PD is the maximum discharge power. Okay. Feasibility and adaptability to the generating source. Highly efficient storage systems needs to be closely adapted to the type of applications and to the type of production. So basically, feasibility and adaptability, it means that all the energy storage devices is are not applicable to all the applications. Okay. So all the each energy storage device are used in a specific application. It is not like where supercapacitor is required, you install a battery in place of supercapacitor and it will work. It doesn't work like that. Depending on what is the requirement of your application, we use energy storage device. So that is basically feasibility and adaptability. Okay. Then self-discharge, portion of the stored energy dissipated during non-use time. You might have seen that if you charge your mobile phones and you don't use it for a day or two, then also its battery will discharge. Or day or two is a longer time. For example, you have seen that your battery is 94 at night. You did not use it at night. You were sleeping and your phone was not in was in the non-use mode. Okay, but when you wake up in the morning, its battery is 80. So that 14% where it is gone, it is basically self-discharge. So every energy storage device has some self-discharge, which is the portion of, self energy dissipation takes place. Mass and volume density refers to the maximum amount of energy stored per unit mass of basically the amount of energy stored per unit mass or per unit volume. Okay. Now, coming on to different types of energy storage systems. So that we will be discussing various energy storage systems. So they are of different types: electrochemical energy storage systems, electrical energy storage systems, chemical energy storage system, thermal energy storage system, and mechanical energy storage system. So electrochemical energy storage systems consist of batteries, then flow batteries, fuel cells. Then electrical energy storage consists of capacitors, then supercapacitors, superconducting magnetic energy storage, that is SMES. Then chemical energy storage devices consist of hydrogen, biofuels, hydrated salts. Then thermal energy storage devices consist of molten salts, then solar ponds, then cryogenic liquid air or nitrogen. Then mechanical energy storage devices consist of flywheels, compressed air energy storage, then pumped hydroelectric storage device. Okay. And what we will be discussing few of them. That is, the one is batteries we will be discussing, then flow batteries we will be discussing, then supercapacitors we will be discussing, then hydrogen energy storage we will be discussing, then molten salt energy storage we will be discussing, and flywheels we will be discussing today. Okay. So coming on to the first one, which is batteries. So what are batteries? Basically, they are electrochemical energy storage devices which stores energy chemically and uses electrochemical reaction to produce electricity at a fixed voltage. Okay. You might have heard about batteries and supercapacitors in your 10th, 12th, in the school time, you might have heard. Okay, so basically, batteries they store energy chemically. Chemical reaction takes place within a battery to store energy. Okay, batteries are suitable for applications that require the supply of relatively large amount of energy storage, that is almost greater than 1 megawatt hour over long periods of time, that is 15 minutes or more, are suitable for application that supply the basically batteries are applicable. Batteries are used where long time energy is required. You need to store, you need energy for a longer time. So basically, their batteries are used where rapid recharge is not necessary and where maintenance can be reasonably performed. So they are not specially suitable for environmentally sensitive sites, remote locations, or applications that require rapid discharge and absorption of energy. Okay. So it has various advantages, that is convenient voltage characteristics, convenient sizing, and extensive design history. And some disadvantages, that is it has a limited cycle life, voltage and current limitations, and often present has environmental hazards because discarding battery is a environmental hazard. Okay, it releases various chemicals into the atmosphere while degradation. Okay. Now coming on to next, that is the flow batteries. So basically, a flow battery operates by passing a solution over a membrane where ions are exchanged to charge and discharge the cell. So here it is a membrane based, ion exchange based membrane, which is basically the separator here, and it operates by passing a solution over the membrane where, and this membrane, it allows the passage of ions but not electrons. Okay, only ions present in the electrolyte can pass through this membrane. No electrons can pass through it. Okay, so for the passing of electron, external mean ions pass through these like membrane, whereas the electrons pass through the external circuit, which in turn, this external movement of electron in the external circuit helps in, is basically the current which is used to light up a load. Okay, is storage capacity the function of the volume of the tank and holding the solution? So basically, the amount of the volume of the electrolyte, which is basically catholyte and anolyte, determines the storage capacity. The more the quantity of electrolyte present in the flow battery, the more is the storage capacity. A flow battery is technically similar to a fuel cell and an electrochemical accumulator cell. Commercial applications are for long half cycle storage, such as backup grid power. Its advantage is flexible layout, long cycle life, no harmful emissions. Okay, need large tanks. It's some disadvantage. Disadvantage is the it needs large tanks to store energy. As I told, that if you increase the volume of the electrolyte, then the storage capacity will increase. So for that purpose, very large tanks are required. That is a disadvantage, and low charge and discharge rate. Okay, because right now batteries have evolved a lot, so we can get, like, we can see that batteries charge within an hour, and you can use them for a longer time. But the ancient battery systems, they used to they had a larger charging time compared to the discharge time. Okay, now, next is the electrochemical or super or ultra capacitors. So here we are discussing them in short, then we will be discussing them in detail also. Okay. Next type of energy storage devices are the electrochemical supercapacitors or ultracapacitors. So electrochemical capacitors are also known as the supercapacitors, ultracapacitors, or electrochemical double layer supercapacitors, so which is famous by the name EDLC. So they store energy in the electrical double layer at an electrode, electrolyte, or interface. So basically, it has one electrode. One, this is anode, this is cathode, and this is the electrolyte, which consists of various ions. So it stores energy at the interface of the electrode and electrolyte. So it will be storing energy at this interface. Okay. The energy and power density of electrochemical capacitors fall between those of the batteries and and conventional supercapacitors. So basically, this thing comes from the Ragon plot. We will be discussing further. It is basically a plot of energy density versus power density. Basically, the energy density determines that how much charge or for how long a energy storage device can deliver power or deliver energy. And power density, basically it means that how easily it gets charged or discharged. Okay, so Ragon plot basically decides that what at what position which energy storage device should is at, depending on its efficiency, depending on its energy density and power density. So basically, supercapacitors, they have high power density, whereas in the case of batteries they have high energy density. uh, what it means is that high energy density, that is, batteries, you can extract energy for a longer time. When battery takes a longer time to get discharged, so that's why it has high energy density. Whereas in the case of supercapacitor, where you need instant energy for a small time, you need a high amount of energy, then you use supercapacitors. Okay, so here we can say that it has high power density. It does not have high energy density because for it discharges very instantly, it discharges very fastly, so that's why it has very low energy density. Okay, so the energy and the power density of the electrochemical capacitors fall between that. So we will be discussing this also, what this line means. So it means basically that the batteries have very good energy density, and capacitors have a good power density. So supercapacitor comes in between, which is basically a good thing because it is giving the like synergistic properties of both batteries and and capacitors here. Okay, so its advantages are high power density, high cycle life, quick recharge. Okay, it gets recharged very fast and discharged also very fast. Okay, matlab it is giving power very easily. Okay, then disadvantages are low energy density and it is expensive compared to battery. Now, next is the hydrogen storage. Among different resources, hydrogen has been recognized as an ideal energy carrier and environment friendly energy source. As we have studied earlier, that hydrogen energy is becoming very famous. It is becoming the very crucial and focus of the energy industry as it is completely environment friendly energy source. So till now we studied the energy hydrogen generation. How do we generate hydrogen? But now we need to study that how do we store it, because as we know that storing hydrogen is also very crucial. So here we will be also discussing about hydrogen storage. We have different methods to produce hydrogen energy, and most efficient way to store energy is in the chemical form. Compared with the liquid and gaseous state, solid state is very reliable method because of safety considerations. In storing hydrogen in the solid state is much safer compared to in the liquid and gaseous state. Advantages is abundant in the earth crust. It is present in very abundance in earth's crust. Then compatibility of hydrogen with fuel cell. Then high efficiency than diesel and gasoline. It has a very high efficiency compared to diesel and gasoline. Then disadvantage is it has a high cost, high flammability, and it is still dependent on fossil fuels. That till now, hydrogen is produced using various fossil fuels only. I mean, we have not still shifted towards completely towards the water electrolysis or the green hydrogen production techniques. Okay. Then the next one is the thermal energy storage. It is defined as the temporary holding of thermal energy in the form of cold or hot substance for later utilization. As we know that thermal energy, we have a lot of sources of thermal energy like geothermal energy or from the fossil fuels or then solar energy. We have lots of resources where thermal energy we can get thermal energy, easy thermal energy. So storing it is also very important. Thermal energy system deals with the storage of energy by cooling, heating, melting, solidifying, or vaporizing a material, and the thermal energy becomes available when the process is reversed. Okay, mean we heat a substance or we heat a liquid, and we like store the energy, store the heat energy within the liquid, and then we whenever heat energy is required, then we bring it in contact with the by using a heat exchanger or by generating steam. We can, for example, if we need heat, we need energy in the form of heat only, then we can use heat exchanger, or if we need to store them in the form of electrical energy, then we can we generate steam, and then that steam can in turn help in the movement of turbine, which is integrated with the uh, electrical generator, so for the which can produce electricity. So TS systems are used particularly in buildings and industrial processes. Its advantages are it helps to cut down electrical bill, green buildings, then highly versatile, and environmental impact is reduced. Energy loss in round trip inefficiencies. It is one of the disadvantages. Then additional cost and complexity and additional infrastructure and space requirement. Okay. Now coming on to another mechanical energy storage device, which is flywheels. So flywheels store energy in the form of momentum in a rotating wheel or cylinder. This cylinder, it keeps on rotating, and the energy which is generated due to the momentum of the rotating wheel, that is stored. Okay. An electric motor spins the rotor to high velocity to charge the flywheel, and during discharge, the motor acts as a generator, converting the rotational energy into electricity. Okay. Power electronics are used to ensure that output voltage has appropriate voltage and frequency characteristics. So it has various advantages. That is, one is high power density, high cycle life, power and energy sizing. Then it has few disadvantages, that is low energy density, large standby losses, and potentially dangerous failure modes. Okay. Now coming on to the nanomaterials for energy storage. So where nanomaterials are required and why they are required, we will be discussing. Smaller size offers a great deal of advantage to the advancement of existing technology and to the exploration and development of new technology. As we have discussed earlier also, that using nanoparticles of a material, or like using catalysts which are nano in size, provides much better advancement and efficiency compared to the larger counterpart of these nanoparticles. Okay. So nanostructure benefits providing a large surface area to boost the electrochemical reaction or molecular absorption occurring at the solid liquid or solid gas interface. So nanoparticles, they provide larger surface area, then generating optical effects that improve the optical absorption in solar cells, then giving rise to high crystallinity or porous structure to facilitate both electron and ion transport and electrolyte diffusion so as to ensure the electrochemical processes occurring efficiently. Delivering new mechanisms, for example, the quantum confinement effect, which lead to the nanostructured materials achieving energy conversion and storage more efficiently. However, while the advantages of nanostructured material have been well documented, there are still some aspects of nanomaterials which needs to be addressed. Now, some of the key challenges related to the nanomaterials. Okay, the challenge for material synthesis is still facing a challenge. I mean, synthesizing these nanoparticles, synthesizing these nanostructures, that too in a controlled fabrication. Because synthesizing nanostructures is very difficult, because it is not like you synthesize and whatever you get, it is in the nano size, so you consider it as nanomaterial. No, all these nanomaterials are, they needs to be synthesized in a controlled atmosphere. Controlled fabrication needs to be done so that it has a desired morphology, structural defects are not there, and surface chemistry is to our advantage. Okay, so it's synthesizing nanoparticles is very crucial. More insightful understanding of the relationship between the device performance and the material structure, with the aim to further develop the merits of nanostructured materials for enhancing the device performance in terms of reaction, activity, optical absorption, and electron or ion transport is needed. Mean we need to. Um, this is also a challenge that like to use the nanostructured materials for enhancing the device properties or device performance in different terms, like in different terms altogether is difficult. Like as we have also mean as we know that only introducing a single nanoparticle will not work all the time. So if anything is possible, or if there is a way that to if there is a way that if you introduce a single nanoparticle, all the required mean two three characteristics are enhanced all at once, then that would be a very good thing. Otherwise, we need to introduce more than one kind of nanoparticle. New mechanisms relying on nanostructure are anticipated to increase the optical absorption and reduce the charge recombination as well as the other energy losses related to electron transport in solar cell, and improve both the energy and power density of lithium ion batteries. So there are various challenges also are associated with the nanostructures which we need to address. Now, some of the solutions which basically researchers are trying nowadays to challenge to rectify these challenges. Okay, so these are surface modification of nanoparticles. So basically, for the specific case of energy storage applications with nanomaterials, surface engineering becomes a critical component. All you can do is, if you do some engineering, if you do some modification to the surface, you can enhance the properties of these nanoparticles manifold. Okay, surface engineering of nanostructure in the context of four mechanistic roles that surface engineering can play. This includes, the first one is chemical activation, which is where the surface layer plays the active role in facilitating a Faradic chemical process. Then other is the solid electrolyte interface control, where a surface layer can lead to a stable artificial interface for Faradic process to occur. Then third is the chemical passivation, first is the chemical activation, then is the chemical passivation, where near atomically thin surface protective layer can protect from corrosion or unwanted electrochemical reactions at interface. Then mechanical stability, where a thin layer can provide mechanical stability support to inhibit fracturing or mechanical failure. So if you could introduce some kind of surface modification to a nanoparticle so that it may help, either you can introduce a surface layer which enhance the Faraday chemical process, or in solid electrolyte interface. In case of solid electrolyte interface, what happens, a surface layer is made on the surface of the nanoparticle which act as a stable artificial interface and assist in Faraday processes. Okay, then surface passivation is you are uh, providing a thin surface coating kind of coating kind of material over the nanoparticle which prevents the corrosion or unwanted electrochemical reactions at interface. Then mechanical stability also can be provided by surface modification. Now, coming on to first one is the chemical activation. For example, chemical activation, it refers to the ability for a surface engineering process to transform a material into a functional template for energy storage. For example, this is a carbon cloth. If you grow, for example, here via annealing, they have grown titanium dioxide nanowires over this template, over this carbon cloth itself. Okay, so by growing this nanoparticles over this carbon cloth itself, they have improved the properties of this carbon cloth. Okay, in many cases, it involves the coating of active material on to a template that is highly optimized for surface area. So what happens when we grow this TiO2 over this carbon cloth? Its surface area increases, then surface area increases, it becomes more porous. So which will help this increased porosity will act as the additional active sites for the Faraday reaction. Okay, that is highly optimized for surface area, electrical conductivity, or ionic transport so that the physical properties and electrochemical properties can be engineered independently. Common ways to achieve this goal include deposition of active material like nanowires, shell arrays, or nanostructured conductive carbon template. So what happens if you grow these TiO2 nanostructure over this carbon cloth itself? This will increase the electrical conductivity of the carbon cloth, as well as the surface area will be increased, and ion transport will also be enhanced. Okay, so this is basically chemical enhanced activation which is done using nanoparticles. Then other is the solid electrolyte interface control. It refers to an irreversible layer that forms along the interface between the electrode and electrolyte in a battery. So basically, suppose this is the electrode, these are two electrodes, and this is electrolyte. So this is the interface we are talking about. Okay, this is the interface. So at this interface, due to the reaction between this electrolyte and electrode, at the interface, there is a formation of an irreversible layer which is called as the solid electrolyte interface. This primarily forms from reduction of the electrolyte on the electrode surface. Reduction of this electrolyte on the electrode surface, SEI, is formed. Composition and function of SEI varies depending on the type and morphology of the electrode and testing parameters. Volumetric expansion of the electrode can expose additional material, causing more SEI to form, irreversible consuming ions and electrolyte while possibly producing gas. The end goal for SEI engineering is to form a stable and ionically conducting surface that enables high rate capability and little degradation over thousands of cycles. So the formation of this SEI, what happens, it forms a stable and ionically conducting surface which further enhances the cyclic stability of the battery. Okay, controlling SEI is particularly important for nanomaterials due to the high surface area and electrolyte exposure in a battery cell. Okay, just a second. Next one is the chemical passivation. So due to the reduced dimension, nanoparticle possesses high surface free charge. As you know, as we have discussed that since nanoparticles have a very small size, so it has an enhanced high surface free energy, and this drives their reactivity in many standard environment. So what happens? The surface passivation, as we discussed, the surface passivation, if you coat a these nanomaterials over something which, so that it, these chemical passivation, basically how nanoparticles are used in chemical passivation. Passivation means like uh, mm, protective. Okay, so basically, if some nanoparticles can form a thin layer over a material to provide it protection from corrosion, making it corrosive resistant. So that is basically chemical passivation. So due to their reduced dimension, nanomaterials possesses high surface free energy, and this drives their reactivity in many standard environments. Where the surface reactivity can be controlled by engineering the SEI layer in battery electrodes, non-ferritic electrochemical supercapacitors are an example of an energy storage device that requires electrode to be chemically inert. Okay, so basically, due to this, most supercapacitor electrodes are produced from nanoscale form of carbon. Okay, it can also be used to engineer the substructure of highly porous nanoscale electrode to increase capacitance, since pore size and capacitance are correlated. So basically, for example, taking this as example, this is pristine PSI. If you coat this pristine PSI with graphene which is a nanoparticle, then it leads to increased conductivity and increased porosity, as well as corrosion resistance is increased. So all this can be done using nanoparticles. Now coming on to mechanical properties, how these nanostructures play a crucial role in increasing the mechanical properties. So the mechanical properties become an important part of an energy storage system that exhibits high storage capacity, since volumetric changes leads to cracking. As you might know that all these energy storage devices, they have this cycle of charging and discharging. So during each charging and discharging, what comes, that is, a volumetric changes takes place. Due to that charging discharging, volumetric expansion or shrinkage takes place, due to which these devices are susceptible to cracking and pulverization of materials without robust and mechanical features. Mean, if the materials don't have good mechanical property, then cracking and pulverization can take place. So they have two strategies to overcome these difficulties: developing nanoscale materials that can accommodate large volume expansion. So introducing some nanomaterials which can accommodate this volume expansion, means shrinkage and expansion can take place can take place easily, and the use of thin surface coating which will act as the elastic glue which holds the material together as it stores the lithium ion. Okay, surface engineering is a tool that can, in addition to chemical modification, provide a mechanical support structure to mitigate the loss of active material. The most effective material combine both of these strategies to overcome these mechanical challenges. Now, coming on to the electrochemical storage systems, which are basically the electrochemical batteries and flow batteries. All these we will be discussing now in detail. So, electrochemical storage systems, often called as the electrochemical batteries, are closed systems able to perform a reversible conversion from chemical to electrical energy. Okay, so basically, batteries are used to store energy in the form of electrical energy. So here chemical energy is converted to electrical energy. We can divide the electrochemical cells into two types. So basically, the first one is electrolytic cell and other is the voltaic cells. So in electrolytical cell, what happen? An externally applied potential drives a current through the cell and causes chemical reactions at the electrode. So here Firstly, we apply an external potential, and that external potential drives current through the cell, and this current causes chemical reactions to occur at the electrode surfaces. Whereas in the case of voltaic cells, chemical reactions occur at the electrodes, and which produces a potential difference between the electrodes that drives the current through the external circuit. Okay. So these are both basically opposite of each other. Okay. In one, we are applying firstly external potential, and then chemical reaction is taking place, and then the other chemical reaction is taking place firstly, which is responsible for driving current through the external circuit. Okay. Coming on to the components in battery system. So basically, there are various components which are present in the batteries. Firstly, the negative electrode, then positive electrode, then electrolyte and separators. So negative electrode, it is to which the anions, that is the negatively charged ions, migrate. As you can see here, this is a negative electrode, this is a positive electrode. Okay. So as we apply potential in the external circuit, what happens is as if you apply potential to the negative electrode, what will happen? The anions will the ions present in the electrolyte will dissociate, and it will migrate to the mean anions will migrate to the anode, that is donating the electron to the external circuit as the cell discharge. Okay. It will donate this electrode will donate an electron in the external circuit, and the anions present in the electrolyte will move towards the migrate towards the anode, whereas the cations present in the electrolyte will migrate towards the cathode. Electrolyte, it is basically containing dissociated salt which enable ion transfer between the two electrodes, providing a mechanism for charge to flow between positive and negative electrodes. And this separator basically mainly we take a polymer membrane, which is basically semi-permeable membrane, which allows the movement of ions but no movement of electrons, due to which the electron moves through the external circuit, and this movement of electron is responsible for the generation of electric current in the external circuit. Okay. Coming on to the elementary principle of battery. So basically, the active mass of an electrochemical cell contains a couple of redox reactions. So redox reaction takes place at the both the electrodes, namely a set of chemical reactions in the reduced form, which is denoted by Red, able to provide electron and to be transformed into another set of chemical species, which is OX, to accept electrons. So at one electrode, reduction takes place, and at other electrode, oxidation takes place. And then ions present in the electrolyte will dissociate and move towards the respective electrode, as the separator does not allow the movement of any electrons. So the electrons move through the external circuit, which is responsible for the movement of current in the external circuit, which is this current is used for the lighting up of load. Okay. A redox reaction is characterized through the potential, and it is potential determined by the Nernst equation. So this Nernst equation is responsible for determining the redox potential. Okay, so it is given by this reaction. This is the Nernst equation. Here, OX and Red, these are the concentration of oxidized and reduced form of redox couples, and then R is the universal gas constant, T is the absolute temperature at which the battery is working, N is the number of electrons which is implicated in the reaction. Basically, there are two reactions which are taking place. One is the oxidation reaction, another is the redox reaction. So the number of electrons which are responsible in each of the reaction, that is the N, and F is the Faraday constant. Coming on to the classification of batteries, so it is of two types: physical energy and chemical energy. So solar batteries are present, then thermal batteries are present, which are physical energy, part of physical energy, and other is the fuel cell, primary battery, and solar secondary battery, which is a part of chemical energy. Okay. And coming on to primary batteries, so basically batteries are of two types: primary batteries and secondary batteries. So primary batteries are basically, they are disposable batteries. They are single time use batteries. They cannot be recharged. They are fabricated. They are charged during their fabrication. They are charged once, and then you use it, and after discharging you cannot recharge it, and it needs to be thrown away. Okay, so they are disposable battery, basically one time use, because their electrochemical reaction cannot be reversed. Okay, they don't have reversible electrochemical reactions. They contain only a fixed amount of reacting compound and can be discharged only once. The reacting compounds are consumed by discharging, and cell cannot be used again. So whatever chemical reaction is taking place, whatever oxidation reduction is taking place inside the battery, it is basically consuming the electrode material, or it is basically consuming the chemicals involved in charging and discharging. So that is why the reacting compounds, they get consumed, and cell cannot be recharged again, so it cannot be used again. Okay, but its discharging time is long, used when long period of storage are required, lower discharge rate than secondary batteries. Secondary batteries discharge faster compared to the primary batteries, and they are used in various applications like smoke detectors, flashlights, remote controls, etc. Okay. Another is the secondary batteries. Secondary batteries are rechargeable batteries. Basically, the electrochemical reactions which are taking place inside the secondary batteries, they are the reversible reactions. The compounds, the reacting compounds, they are not getting consumed. They are just getting oxidized, then reduced, oxidized, then reduced. Okay. So it is a reversible procedure. Basically, they are redox active materials. So secondary batteries are rechargeable because their electrochemical reactions can be reversed by applying a certain voltage to the battery in the opposite direction of the discharge. Okay. The process can be reversed hundred to thousands of times. So we can say that it has hundreds or thousands of cycle life, means cycle life of at least 100 to 1000 cycles, so that the lifetime of the cell can be extended. This is a fundamental advantage, especially as the cost of a secondary cell is normally much higher compared to a primary cell. Compared to that, coming on to the cost, since these secondary batteries are rechargeable, their cost is also much higher compared to the primary batteries. Okay, furthermore, the resulting environmental friendliness should be taken into account. So, since these secondary batteries, they can be used for a longer time, so they are also reducing the environmental stress. They are reducing the stress over the environment, due to which is imposed by the primary batteries, since they are responsible for releasing various chemicals during their degradation. Okay. Now, difference between them is primary batteries, the cell reaction is irreversible, whereas in the case of cell reaction is reversible. It must be discarded after use. It can be recharged. Have relatively short shelf life, relatively longer shelf life. Functions only as galvanic cells, and functions both as galvanic cell as well as electrolytic cell. They cannot be used as storage devices, since they are only, it is like single time use, energy stored for one time, then it needs to be thrown away, whereas here recharging takes place, so it is basically a proper energy storage device. So examples are dry cell, nickel
Nickel
cadmium
cadmium
battery,
battery is
and for
rechargeable
the
battery.
secondary battery, examples are lithium manganese oxides or lead acid batteries.
Ma'am, nickel cadmium
Now
battery is a
coming on to
rechargeable
different
battery.
types of accumulators. Electrochemical accumulators are charged by converting. Accumulators are basically Electrochemical accumulators are charged by converting the electrical energy into chemical one, and are discharged by an inverse transformation. So basically, there are different types of accumulators. That is, with some are with aqueous electrolyte, some are with non-aqueous electrolyte, and some are large size accumulators. So in aqueous electrolyte, we will be discussing the alkaline accumulators. In the non-aqueous electrolyte, we will be discussing lithium ion accumulator, and in case of large size accumulator, we will be discussing vanadium redox flow batteries. So coming on to the first one, that is the alkaline accumulator. So what is alkaline accumulator? These are basically primary batteries. Okay. So primary batteries, as I told, they are non-rechargeable. single time use. Okay. So the alkaline accumulators are primary batteries based on zinc manganese pair of active materials. Okay. The chemical reaction, so basically, one is manganese dioxide, one electrode is manganese dioxide, and another electrode is zinc. Okay, so both the reactions at like one electrode will be getting oxidized, another electrode will be getting reduced, and due to which the charging discharging of the battery takes place. But here, as I have told, this is a primary battery. So in this case, electrodes during each reduction and oxidation reaction, electrodes get consumed. So the zinc and manganese oxides get consumed, due to which it cannot be recharged. The chemical reaction in the alkaline batteries produce electricity when the manganese dioxide cathode is reduced and zinc anode becomes oxidized. So here, this is the anode, here zinc is getting oxidized, and this is the cathode, here manganese is getting reduced, and this is the total reaction which is producing a potential of 1.5 volt. So the electron generated during the reaction are used to power devices in the electrical external path during discharge. Okay, the rate of the reaction is dependent on the quality of the raw materials and availability of water and hydroxyl ion during the reaction. Alkaline battery is an improved dry battery. Dry battery is basically the electrolyte is basically solid, and flow battery is basically the electrolyte is liquid. Okay. The alkaline battery gets its name because it has an alkaline electrolyte. It has an alkaline electrolyte, that is the KOH paste. KOH paste, so it is solid. So that's why it is a dry battery. Zinc in a powered form increases the surface area of the anode, allowing more particle intercalation. Okay. So it has few advantages, like it has high energy density, longer lifespan, relatively safer and fewer risk, made from non-toxic chemicals. Okay. And its disadvantage are they are bulkier and heavier, higher internal resistance, and battery can leak, and leaked material can corrode circuits when left in device for too long. As you might have seen, though, batteries which we used to use, the single time batteries in the like in the remote controls and etc., you might have seen that if you leave these batteries for a longer time, there used to be some brownish material which used to come out of the batteries. So that is basically, if you keep those batteries for longer time, there is a risk of leakage of the electrolyte paste or electrolyte paste or electrode material. So that is basically a hazard to the environment. Now coming on to the lithium ion accumulator, which is a lithium ion battery, which is currently very famous. The lithium ion concept uses two materials that allows the reversible exchange of lithium ions. The negative ion, that is anode. So anode, it is basically graphite. Anode is it is a thin layer of graphite which atoms of lithium have been inserted. Then for the electrode, positive electrode is the lithium cobalt oxide. Okay, a lithium cobalt oxide, that is a lithium oxide of transition metal, and the liquid electrolyte is basically a hexafluorophosphate of lithium, which is a lithium salt mixed with a solution of carbonate mixture. Basically we take propylene carbonate. This is the solvent basically, and this lithium perchlorate is dissolved in this. So that is the basically our electrolyte system. Lithium ion cell presents very high energy density, up to 200 watt hour per kg. Their typical potential is 3.7 volt. So basically what happens, this graphite anode, it gets oxidized, and what happens, this electrode which is LiPF6, the when we apply potential in the external circuit, what happens, one electrode gets oxidized, other gets reduced, and due to that the electrolytes which are present in the ions present in the electrolyte, they intercalate and de-intercalate from in between these layers. So these are basically the graphite layers, and these are basically the LiCO CO twice, that is lithium cobalt oxide layers. So during each charging discharging, these are the lithium ions, Li positive, they intercalate, that is basically move in, and deintercalate, move out of the uh, electrode. due to which charging discharging takes place. And it has this lithium ion cells. This is a rechargeable battery, and it has a very high current, high energy density of 200 watt hour per kg, and it has a typical potential, provides a typical potential of 3.7 volt. Okay, then it has advantages like high energy density, low self discharge rate, low maintenance to ensure their performance, small and lightweight. Okay, disadvantages: it is hazardous when transported. And moreover, like after the usage of these lithium ion batteries, discard of this lithium releases various chemicals into the atmosphere. That is also a problem. Natural degradation after certain cycles of operation. Then these are sensitive to higher temperatures, and these batteries are costly. Okay. Now coming on to the vanadium redox flow batteries. Redox flow batteries are very promising, and vanadium redox flow batteries are the most developed and most close to commercialization. So why redox flow batteries? Because in this case, the electrolyte is like liquid based electrolyte, and these are also both the electrodes are also in the liquid form. Okay, they are basically liquid uh, solutions. A vanadium redox flow batteries has two chambers, one this and one this. Positive chamber and a negative chamber separated by a ion exchange membrane. So this is ion exchange membrane. Both these chambers are separated by this ion exchange membranes. These two chambers are circulated with electrolyte. Electrolyte gets circulated in this circuit and in this circuit using this pump. Since all this electrolyte and these solutions are in liquid state, so pump is used for pumping them. Two chambers are circulated with electrolyte containing active. These electrolyte consist of active species of vanadium in different valence states, that is VO2 1 positive and VO2 positive in the positive electrolyte, and V2 positive to V3 positive in the negative electrolyte. During discharge, VO2 positive is reduced to VO2 positive at the positive electrode, and V2 positive is oxidized to V3 positive at the negative electrode. So these are the reactions taking place at the anode and cathode, and this is the total reaction. So advantages is high energy efficiency, short response time, and long cycle life, independently tunable power rating and energy capacity. And whereas the disadvantage is low volumetric energy storage capacity, limited by the solubilities of the active species in the electrolyte. So if the active species in the electrolyte are less, then that becomes a limitation. Using expensive ion exchange membranes. So this ion exchange membranes, they are sometimes expensive. Coming on to the factors affecting batteries performance and life. So some of the factors are: the surface area of the electrode should be good, water and acid absorption rate needs to be checked, then temperature of operation is also a crucial factor, then composition of paste and electrolyte, formation and initial charging methods. Now coming on to the aging of electrochemical batteries. So electrochemical batteries, they age too, depending some of the factors. That is the anode side. Anode is the best known component in lithium ion batteries and consists in most cases of carbon. Mostly anode is carbon based materials like graphite or hard carbon. For these materials, the dominant aging effect are basically known and can be separated in three parts. So these carbon based material, they have some aging effects, that is the surface film formation on the particle takes place, degradation of the active material can take place, and lithium metal deposition on the anode surface can take place. Okay, now, cathode side, basically the aging effect of the cathode and especially for the new material are less known but can be summarized. Aging of the active material or surface film formation, mean whatever can take place, what things can take place that leads to the aging of electrochemical batteries. So basically the simplest thing is either some kind of surface film formation can take place on the electrode, or degradation of the electrode active material can take place. So that is the simplest thing, and the intercalation of aging products within the negative electrode. As I told, with each charging, discharging, intercalation and de-intercalation of ions takes place. So that can also be a that may lead to the expansion and shrinkage of the electrode material, that is also responsible for aging of electrochemical batteries. How can nanotechnology improve battery performance? Using nanotechnology in the manufacture of batteries, reducing the possibility of battery catching fire, mean, as we know, batteries can are prone to catching fire. So if we introduce some kind of fire retardant nanoparticle coating or something, then that can be a benefit. To find material suitable for use as electrode with high surface area, this allow charge to flow more freely, reducing is resulting in higher capacity and short charge discharge cycles. Nanostructured materials can offer a huge step increase in surface area for electrolyte material, and nanoparticles could enhance the conductivity of ceramics or gel. Means sometimes when these electrolytes mean lot of research is going on to replace liquid electrolytes, so we can uh, use nanoparticles to enhance the conductivity of some ceramics or gels, so that we can replace these ceramics or gel with the liquid electrolyte, reducing or eliminating the chance of short circuit. Okay. Now coming on to the nanomaterial used in batteries. So for electrode materials, there are various nanomaterials used. That is, the carbon-coated silicon nanowires can be used, carbon nanotubes can be used. Then lithium manganese or lithium cobalt oxide nanoparticles can be used. Lithium alloy or graphene foil can be used. Then phosphorine and graphene hybrid materials can also used. For electrolyte materials, there are various materials that can be used as electrolyte. That is alumina, silica, or zirconium oxide nanoparticles. If they are added to solid polymer gel, then they can enhance the conductivity and storage capacity of the electrolyte. Then solid ceramics have also been explored, as their high temperature resistance would suit demanding high stress applications like large vehicles or renewable power stations. Then 2D molybdenum disulfide is used as an efficient protective layer for lithium metal anode in high performance lithium sulfide batteries. Conductivity of polyethylene oxide based polymer electrolytes can be improved by addition of nano-sized ceramic powders, including titanium dioxide, silicon dioxide, alumina, manganese oxide, or barium titanium trioxide. Much of the research into nano-enhanced batteries in the coming few years will focus on the reducing the cost of these nanoparticles, making them viable for large-scale commercial applications. These are some of the applications where rechargeable batteries are highly used. Now coming on to the supercapacitors. So this is basically the introduction, like the rapid increase in the global energy consumption and environmental impact of traditional energy storage or energy resources have led to tremendously increased research activities on clean and renewable energy sources. So for that clean and energy renewable sources, various energy storage devices are required, and out of which supercapacitors are an efficient energy storage technique. So we will be discussing energy like supercapacitors firstly. So before supercapacitors, we will need to know what is capacitor. So capacitor is an electronic component which is used to store charge in the form of electrical potential. So capacitor, it consists of two plates, basically two plates which is separated by from each other by few millimeters. So the distance between them, it is few. This d is few millimeters. Okay. Amount of charge stored in the capacitor is known as the capacitance of capacitor, and it depends on the dimension of the capacitor. So it depends on the dimension of these electrodes, the amount of charge it can store. When a capacitor is attached across a battery, when we suppose provide potential to a battery to a plate, when a capacitor is attached across a battery, an electric field develops across the dielectric, causing when we apply potential, this positive plate positive charge to causing positive charge to collect on one plate. For example, this is positive plate, this is the negative plate. So when we apply potential, this positive plate, this is the positive plate. So all the negative charge sorry, when a capacitor is attached across the battery, electric field develops across the dielectric. This is across the dielectric, causing positive charge to collect on one plate. All the positive charge it gets collected on one plate. So this is the positive plate, and this is the negative plate. All the negative charge gets accumulated on the counter plate. And the capacitance increases or decreases, changing dimension of the capacitor and material used. So the amount of charge that gets stored, it depends basically on the material of these electrode plates, as well as the distance between them and the size of these uh, electrode plates. So what is a supercapacitor? Basically, supercapacitors are specially designed capacitors which has huge capacitance value and energy density compared to capacitors. Okay, the principle of energy storage in supercapacitor is a pure charge storage on an electrode electrolyte interface electrostatically by it is done in two mechanisms, EDLC and pseudocapacitor. So the EDLC is basically purely when charge gets attracted towards the charge gets electrostatically attracted or at the electrode electrolyte interface by electrochemical double layer capacitance. So when external these are supposed two in electrodes, anode and cathode. This is the collector and these are anode and cathode. This is the electrolyte which consists of various ions. So if we apply potential in to these electrodes, and then what happen, this is the anode. All the positive charge from the battery, sorry, from the electrolyte, it gets electrostatically attracted to the surface of the anode, and all the negative charge gets attracted to the surface of the cathode. And after that, after all the positive charge gets attracted here, then the negative charge comes, then then positive charge. So with each layer, the distance between the two electrode is decreasing. For example, this is negative, then here positive will come, here negative will come, then again negative, then again positive. So with each passing time, the distance between this both the electrodes is uh, decreasing, and with the decrease in the distance, the capacitance increases manifold. So that is why these supercapacitors have very huge capacitance compared to the capacitors. Okay, so this is basically electrostatic non-faradic energy storage, and it can then second mechanism is a pseudocapacitor, where it can transfer a charge to the layer of redox molecule on the surface of the electrode. In case of pseudocapacitor, redox reaction takes place at the interface of the electrode and electrolyte. Okay.
So in this particular lecture, basically we have discussing into two parts. One is called the energy harvesting.
Supercapacitor cells are able to fill the gap between the conventional
so in the point of harvesting systems, we have first discussed
and
the solar energy
batteries.
harvesting.
As
So
I
we
was
discussed about
talking,
importance, different
Raghun
generations
plot.
of
So
solar
this
energy,
is the
different
Raghun
nanotubes
plot
used in the
basically.
solar energy. First generation solar cells are wafer based, whereas second and third generation
Energy
solar cells are
density
fused based.
versus power
Perovskite solar
density.
cells are
So
recent. They achieved efficiencies of
as
3.8%
we
in
know,
2009 to
capacitors have very high
23.3% in
power
2018.
density
So
but
within
low
9 years,
energy
they
density,
have
whereas
reached
batteries
almost
have
20%
very
extra.
good energy
Solar thermal
density but
technology uses
low
sunlight
power
to be concentrated
density.
onto the receiver tubes, in
So
which
in
the
the
heat transfer
case of
fluid gets heated up, which is used in running the turbine.
supercapacitors
Different
fill the
nanomaterials are
gap
added to the base
between
fluids to improve the
capacitors and
thermal properties of
batteries,
heat transfer
since they
fluids.
have
So basically, this is
comparative
will give you
energy
a
density
brief
as well
summary of
as
that solar energy
power
harvesting system.
density
Next, we have
compared
discussed about
to
the hydrogen energy generations. So hydrogen has
capacitors
highest energy
and
content per unit of
batteries.
mass of
Okay.
any chemical fuel and can be substituted hydrocarbon in a broad range of
Now,
applications. Discussed
coming
about
on to
different
type
hydrogen
of
energy generation procedures for
supercapacitors.
fossil fuels and
So there are
biomass,
three types of
thermochemical, electrolysis, biological, solar,
supercapacitors. One is
hydrogen
the
productions. Waste
EDLC, that
processing
is
of methane,
non-ferritic
like natural
process,
gas, is the most common commercial
pseudocapacitor,
hydrogen
that is
production
the
technology
ferritic
today.
process, and
Thermochemical
hybrid
water splitting is the conversion of
capacitors,
water into
that is
hydrogen
a
and oxygen
mixture
by a
of
series
both
of thermally driven chemical reactions.
EDLC
Pyrolytic
and
conversion of substrates to
pseudocapacitor. So
hydrogen is a
in
complex
case of
biochemical process
EDLC,
manifested by diverse groups of bacteria by a
electrodes
series of
used
biochemical
are the
reactions under
carbon-based material, that
anaerobic
is
conditions.
activated
So
carbon,
basically, we
carbon
have discussed all
nanotubes,
these
then
things in that
graphene.
particular hydrogen
Whereas in
energy
the
generation
case of
part. Next, we have
pseudocapacitors,
discussed about the energy harvesting
electrodes
by nanogenerators.
sometimes
A nanogenerator is a type of device
conducting
that converts
polymers are
mechanical
used,
or maybe the
then
thermal energy as
metal
produced by
oxides
small
are
scale physical
used.
change into
In the
electricity.
case of
Zinc oxide,
hybrid
cadmium sulfide,
capacitors,
gallium nitride,
composite
PGM piezoelectric
hybrids,
materials, and the
asymmetric
PVDF,
hybrids, or
polyvinylidene
battery type
dichloride, are
hybrids
the
are
mostly
used.
used materials for
Okay.
piezoelectric nanogenerators.
Now coming on to
Ferroelectric
the
nanogenerators,
criteria
which
for
is based on the
choosing
frictions, because drive force demonstrations,
nanomaterial
lots of
for
contact electrifications and
supercapacitors. For
electrostatic inductance,
electrode
and they
material,
can be
they
coupled
should
with
have
piezoelectric, pyroelectric, thermoelectric nanogenerators to get more output.
high
That means this is a certain kind
cyclability,
of hybrid kind of
long-term
nanogenerators.
stability should be
Thermoelectric
there,
and pyroelectric energy
good
harvesting techniques are
surface
generally used
area
to
should
harvest
be there,
waste
then
heat
high
energy.
electrical
Conventional source of energy are
conductivity,
non-renewable
resistance to
and
electrochemical
non-conventional source of energy are renewable
oxidation
source of energy.
or
So we have
reduction,
discussed all these
and
things in that particular energy harvesting by
high
the nanogenerator
temperature
part. Next, we
stability
have
should
discussed
be
about the
there.
energy storage systems. Now we have generated the energy. Now we are going to store that particular energy. How to do that? The intermediate nature of renewable sources like solar and wind need storage to deliver
Then
the right amount of power at right
electrolyte
quality.
materials,
Performance
they
of
should
batteries
have
can be enhanced
high
by finding
ionic
suitable materials for use as
conductivity,
electrodes with
low
as high surface
viscosity to
area as
access
possible.
small
Supercapacitor cells are able to fill the gap
to
between
access
conventional
small
capacitors
pores.
and batteries by providing high power
Then
performance
chemical
in a compact
stability should be
design.
good,
Properties
easy
like large surface
availability,
area,
and
poor
cost
structure, mechanical strength,
effectiveness
and
should be
stability are
there.
ideal parameters for an efficient hydrogen storage
Coming on to
material
the
because the gas can be
EDLC,
stored
as I told,
inside the porous
EDLC, they are
materials. It can
constructed
make a
using
trap
two
kind of things.
carbon-based
Thermal energy
materials
storage can be
as
possible by
electrodes and
sensible heat storage,
electrolyte
solid or liquid
and
media,
a
latent heat
separator.
storage, phase change materials,
So
or by the chemical
carbon-based
reactions,
materials
which
are
we have
electrode, then
discussed
a
the first part
electrolyte
of
is
this
there,
particular
and a
lecture.
separator is there.
Now, I am going to discuss a
EDLC
little bit
can
about our
either
lab. So
store
basically, in
charge
our lab, we are working as a
electrostatically
whole group,
or
and the
via
whole group
non-ferritic
are working
process. So
into different
basically,
applications.
this is
Basically, we are
simply
working on the
electrostatic
energy storage
attraction of
device, energy generation device.
opposite
We are working on the
charges on
sensors.
the
We are working on
surface
the
or on the
we are
interface
working
of
on the
the
biopolymers,
electrode
we
and
are working on the
electrolytes.
materials
Okay,
for orthopedic
so
implants,
suppose
we are
this
working
is
for
the
the materials for
positive
the
charge
aerospace industry. But
electrode,
basically, our
electrode.
main specialization
Then
is that
the
to synthesize
negative
the
charge
different types of
from the
nanofillers,
electrolyte
modifying those
gets
nanofillers, or making some kind of new composite
electrostatically
systems which can
attracted
sustain
on
into
the
all those
surface
applications. So
of
at the
the
onset, we are working
positively
on the
charged,
advanced synthesis
and
and
vice
surface
versa
modifications of
takes place
nanofillers,
on
like
the
we are working on
other
the carbon nanotubes.
electrode.
Graphene
Okay,
already we have made
so
the graphene,
basically
and we
which
have derived certain kind
it
of
involves
new
no
technology which is
transfer
called
of
instant
charge
Hamas
between the
method,
electrode
that
and
by which we are
electrolyte.
making
So
the
there
reduced graphene
is
oxides. We
no
are working on the carbon parts,
electrochemical
we are working on
reduction
the
or
good nanorods,
oxidation
good
takes place,
nanoparticles,
or
we are using on the
no
graphene nanoribbons,
chemical
metal
reaction
oxides
taking
basically we are
place
using,
between the
we are using
electrode
on the
and
transition metal
electrolyte here.
dicarbonate,
Okay,
and nowadays also we are working on
EDLC
the metal
utilizes an
organic framework.
electrochemical
Also
double
we are
layer
working on
of
the advanced
charge to
nanomaterials for the
store
high performance
energy.
sensors.
As
Basically we are
voltage
working
is
on the glucose
applied,
sensor,
charge
humidity sensor,
accumulates
and
on the
some kind of
surface,
toxic gas sensors. We are
electrode
working on the
surface,
energy
and
harvesting
ions in
systems,
the
that is
electrolyte
basically on the nano generators and
solution
the energy storage
diffuses
systems.
across
Basically we
the
are working on the
separator
fluidable
into the
supercapacitor,
pores of
hybrid
the
storage systems, polymer electrolyte membranes.
these
And also another part, we are working on the
ions
biopolymers
from
and the
the
bionanomaterials.
electrolyte.
Basically, we
They
are dealing with the
only
targeted
get
drug delivery for the breast cancer and for basically for the lung cancer.
electrostatically
We are working on the orthopedic
uh,
implants. Basically, we are using the magnesium alloy for making any
absorbed
kind of
on
knee
the
joint or in the hip
surface
joint.
or on
We
the
are working on
pores
the
of the
barrier and the thick
electrode
packaging
of
systems.
opposite
So basically,
charge.
we can keep the food for
However,
a
the
longer time.
electrodes are
And overall,
engineered
basically,
to
we are working on
prevent
the
the
blending calculations
recombination
and
of the
compatibilizations of
ions.
polymer and metal matrix
Mean
nanomaterials for the advanced applications. We did certain
these
work on the
electrodes
aerospace
are
applications, like for the aluminum
engineered
metal
in a
matrix
way
composites.
that
We did work certain kind of
though
polymeric nanocomposites, basically for
negative
the
charge
automotive
mean
parts like
though
car bumpers
opposite
or maybe like
charges are
car
getting
bonnet systems. So basically,
electrostatically
this is the website where you
attracted,
can
but
get
they are
the
not
information
getting
about our lab and actually what we are doing, and
recombined.
also you
Okay,
can get certain kind of publications details
thus
over there, and it will give you
the
a whole summary
double
of
layer of
our
charge
particular
is
lab.
produced at
So this
each
is basically the
electrode.
group members.
These
So as
double
a team,
layers,
basically we are
coupled with
working
an
all
increase
together.
in
So there is
surface
nothing like
area
any
and
hierarchy over
decrease
there.
in
So
the
being a
distance
team
between
member,
the
basically
electrodes
we are
allow
working. So
EDLC
now
to
our
achieve
group
high
consists
energy
almost
density
like
than
14 to 15 people. So
conventional
basically we are working together and we are trying to do this kind of
capacitors.
research. Thank
Okay,
you very much for your patience.
so these are some of the electrode materials which are very famous. As I told, this EDLCs are only responsible. Normally they use carbon-based materials as electrodes. So activated carbon is one of the widely used electrode material in supercapacitors. So conventional electrode material for the EDLC are porous activated carbon with large surface area. Charge accumulation and capability of carbon materials at the electrolyte surface is increased with their specific surface area. And however, specific capacitance is not always linearly increased because of the wide pore size distribution. Okay, so these electrode materials I'm not discussing in much detail because I have a lot to explain till now. Okay, so these are basically you can read. These are simply the like general information regarding these nanomaterials. So the another is carbon nanotube. These we have discussed earlier also, this carbon nanotube and all, but I'll be giving a brief gist. Okay, the carbon nanomaterials, because of the inherent high electrical conductivity and chemical stability, carbon nanotubes have been considered as promising electrode for supercapacitors. Carbon nanotubes are produced by catalytic decomposition of some hydrocarbons and by carefully manipulating different parameters. So CNTs can be sometimes CNT can be chemically activated with the KOH in order to improve its specific capacitance. So it is not like simply these nanoparticles are used as electrode materials. We can, as I told, that surface modification or activation also can be done. Basically, right now researchers are uh, currently lot of research is going in this field in the electrode development of the supercapacitors and batteries. So these are some of the conventional nanomaterials which were used, but now researchers are trying to improve. Either they are trying to functionalize these conventionally used electrode materials, or they are trying to develop new electrode materials so that uh, so that the specific capacitance of the of these electrode materials can be increased. Okay, now graphene with high electrical conductivity and charge transport mobility, graphene is attracting extensive attention as an electrode material for high power EDLCs. Graphene nanosheets grown on a current collector exhibited a high power performance that is even close to that of the conventional dielectric capacitors. Okay, so researchers are working on porous graphene oxide preparation by KOH activation, and different methods are used for the synthesis of graphene. For example, thermal exfoliation of graphitic oxide. Basically, graphitic oxide, if you keep it at 300 degrees C for 6 hours, then the sheets get these are basically graphite sheets at different distance and at a longer distance. But if you keep these at 300 degrees C for 6 hours, then you can get single sheet. That is single graphite sheet is basically graphene. Okay. Heating nano diamond at 1650 degree C in a helium atmosphere, then camphor decomposition over nickel nanoparticles. So these three are the uh, synthesis techniques of graphene. Apart from them, also there are many techniques. So these are some of the techniques that we have discussed here. Not in detail, I'm just telling these are some of the techniques for synthesis of graphene. So coming on to some of the advantages of supercapacitors, higher energy density than conventional capacitors, no chemical or structural change during charge storage, work in extreme temperature and are very safe and have high cyclic stability. It has some of the it has disadvantage that it cannot match energy density of mid-level batteries because limited surface area and poor size distribution of conventional electrode materials. Even though it has shown good energy density, but still it is not matching to the energy density of batteries. Okay. Now, another is the pseudo-capacitors. Pseudo-capacitors, it stores charge faradically through the transfer of charge between electrode and electrolyte. So there was no charge transfer was taking place between the electrode and electrolyte, but here at the surface of interface of the electrode and electrolyte, charge transfer is taking place between the electrode and electrolyte. So this is accomplished through under potential deposition or reduction oxidation reaction or intercalation process. Okay. So these Faradic processes may allow pseudocapacitor to achieve greater capacitance and energy density than ADLC. It involves redox. There no reduction or oxidation was taking place in the case of ADLC, but here reduction and oxidation reactions are taking place, which is similar to batteries. That is why it can be a way to increase its energy density. Okay. Its construction is similar to ADLC, but the electrodes are made from metal oxides or conducting polymers. Basically, here electrodes we are taking different, that is metal oxide and conducting polymers. Why? Because here oxidation and reduction are taking place. So therefore, we are taking redox active material as electrode materials, whereas in the case of ADLC, carbon-based materials were taken which are not redox active. Their only electrostatic attraction was required, which is easily possible in carbon-based materials, whereas in the case of pseudocapacitors, metal oxides and conducting polymers are used, which are redox active. That's why reduction and oxidation reaction can easily take place and charge storage can take place. Okay. Coming on to the mechanism, as I already told, it is basically the mechanism is reduction. There are three mechanisms: under potential deposition or reduction oxidation reaction and intercalation process. So basically, under potential deposition occurs when metal ions form an adsorbed monolayer at a different metal surface. So here, suppose this is the current collector. Here, it is coated with gold electrode, and on application of the potential, this metal ions get deposited. This gold metal ions are deposited over the current electrode. Then lead monolayer is deposited over gold electrode. And then this lead electrode, it takes part in the reduction and oxidation reaction. Okay. One glass. One classic example of under potential deposition is the lead on the surface of gold electrode. Okay, redox pseudocapacitance occurs when ions are electrochemically adsorbed onto the surface or near the surface of the material with the resulting Faradic charge transfer. Intercalation pseudocapacitance basically occurs when ions intercalate into the tunnel or layers of the redox active materials. And this redox active is basically simply at the surface of the electrode and electrolyte, at the interface of the electrode and electrolyte. Oxidation and reduction reaction takes place, which is similar to the battery. And other third type of mechanism is the intercalation pseudocapacitance. That is simply the ions present in the electrolyte gets intercalated or deintercalated from the electrode surface. Okay. And during this intercalation and deintercalation, no crystallographic phase change take place in the electrode material. Coming on to another type of electrode material, that is the conducting polymers. So nowadays various conducting polymers such as polyacetylene, one of the most famous is the polyaniline, then polypyrrole, polythiophene, then P dot have been considered as promising pseudo capacitive electrode materials for supercapacitors. They offer capacitive behavior through redox reactions that occur on the surface and throughout the entire bulk. And the redox process are highly reversible because no structural change such as phase transformation happen during the redox reaction. Most widely used are the polyaniline polypyrrole, and currently in our lab also we are working on these conducting polymers also. I myself am working in the conducting polymers to use them as electrode material in supercapacitors. So we in our lab we are working in polyaniline as well as polypyrrole, and I am working on polythiophene. Okay. So the conducting polymers may swell and shrink in the process of intercalation and deintercalation, which often results in a low cyclic stability when they are used in supercapacitor. So the problem with here we are discussing the problem with conducting polymers. So the only problem with conducting polymers is that these conducting polymers, they have a tendency to swell and shrink with each charging and discharging cycle, due to which leads to the low cyclic stability. So that is the currently the area of research in the conducting polymers. Though conducting polymers have good redox activities and are good redox have good redox properties to use them as electrode material, but the enhancement of the cyclic stability needs to be done, needs to be researched. Okay. Then other type of electrode material is metal oxide. Metal oxide, they generally have high spatial capacitance compared to the carbon materials for EDLC. They have high spatial capacitance, and during the initially basically the in initially these metal oxides were only used for the as electrode materials, but nowadays people are shifting from metal oxides to like conducting polymers. Okay. So they have various advantages like pseudocapacitance. Pseudocapacitor has various advantages like higher energy density than ADLC. Hydrous ruthenium oxides can achieve extraordinary capacitance, but it has various disadvantages also, that is lower power density than ADLC. Cycle life can be limited by mechanical stress and caused during reduction and oxidation reaction. Negatively charged conducting polymer electrodes are not very efficient, and the best metal oxide electrodes are very expensive and require aqueous electrolyte, which means lower voltage. Okay. Now coming on to the hybrid capacitors. So hybrid capacitors, they are basically the mixture of both. They consist of combination of EDLC and pseudocapacitors. So basically in the case of EDLC and pseudocapacitor, both the electrodes are of same material, that is symmetric. Basically both are either carbon, activated carbon, or both are either conducting polymer or metal oxide. But in the case of hybrid, one is carbon based material and other is either metal oxides or conducting polymer. Okay. So here EDLC mechanism will take place, and here pseudocapacitance mechanism will take place. So that is basically a hybrid supercapacitor. The limiting property of it. So in this case, what will happen? The disadvantage of both EDLC and supercapacitors will be overshadowed. All the together leads to overshadowing of the limitations of the combined components, with an advantage of delivering higher capacitance. Hybrid supercapacitors, when composed of two different electrodes made of different materials, shows better electrochemical behavior than the individual ones. Researchers have focused on three types of hybrid capacitors distinguished by electrode configuration, that is composite, asymmetric, and battery type respectively. So basically three type of electrodes are used. Either we take use either composite electrodes are used, carbon based materials with either metal oxides or conducting polymer in a single electrode. As I told, that one will be one electrolyte will be carbon based, other will be polymer electrolyte, or sorry, conducting polymer or metal based. Then asymmetric hybrid combine non-Faradic and Faradic by coupling EDLC and pseudocapacitor. They are set in a way that carbon material is used as negative electrolyte, while metal oxide or conducting polymer as positive electrolyte. Then battery type hybrid combines two different type of electrolyte, a supercapacitor electrode with battery electrode. Okay. So basically a supercapacitor electrode, for example, here we take carbon based material, and then on the other side we take a battery type, that is either LiCO2. Okay. Then coming on to advantages and disadvantages, it has have the most flexible performance characteristics of any supercapacitor. It fits the widest range of application, can achieve very high energy and power densities without the sacrifices in cyclic stability and affordability. And disadvantages are relatively new and unproven technology, and more research is needed to better understand the full potential of hybrid capacitors. So there is not lots of research done till now on hybrid capacitors, so it needs to be done before moving up to the commercialization. It has like very good scope of research. Now coming on to the electrolyte materials, so there are various electrolyte materials including solvent and salt in one of the most important constituents of electrochemical supercapacitor. It is a very important element of supercapacitor. So various types of electrolytes are used. Some are organic electrolytes are also used. Aqueous electrolytes are also used. Ionic liquids can be used, and solid state polymer gel electrolytes are also used because right now like electrolyte research in electrolyte field is basically to shift from liquid based batteries and supercapacitors to solid state batteries, since liquid electrolyte has many problems, leakage and lithiation and different other problems are there, dendrite formation. So that is why we sometimes now we are people are shifting towards dry polymer based electrolytes, also gel polymer based electrolytes and polyelectrolytes also. Okay. Organic electrolytes, they are mainly propylene carbonate, then TBAP, acetonitrile or propylene carbonate, then aqueous electrolyte is H2SO4, KOH or Na2SO4, and then ionic liquids are pyrrolidinium, imidazolium, and aliphatic quaternary ammonium salts coupled with such as anions such as BF6 and BF4. These are some of the applications where supercapacitors are used. Now coming on to the other kind of energy storage, that is the hydrogen energy storage. So let me skip the introduction and move towards the exact thing. So basically, hydrogen storage. Basically, till now we talked about hydrogen generation, how to do the hydrogen generation, but now how to store this hydrogen energy so that it can be used at later time. So it is stored. How do the energy hydrogen storage is measured? Basically, it is measured in two ways, that is the gravimetric density and volumetric density. So basically, the weight percentage of hydrogen stored to the total weight of the system. Total weight, basically the weight of the hydrogen and the container in which it is stored. So basically, the weight of hydrogen upon weight of hydrogen plus container in which it is stored. Okay. And in the case of volumetric density, it is basically the stored hydrogen mass per unit volume of the system. Okay. So there are various characterization techniques to determine the storage of hydrogen. These are the Sievert's technique, gravimetric technique, secondary ion mass spectroscopy, thermal desorption spectroscopy, neutron scattering, and electrochemical characterization. We will be discussing them in brief. So Sievert's technique, it is in this technique basically, uh, just a second. Okay, I'll see to it and let you know. Can you guys give me a 2 minutes break? I'll just be back. Just give me a 2 minutes break. Okay. So coming on to the Sievert's technique. Okay. These are basically some of the techniques which are used to characterize characterize the hydrogen storage. Okay. So Sievert's technique, in this technique, pressure change due to volume change and hydrogen adsorption or desorption of sample will be measured when the valve between the reference volume and sample cell is opened. So, for example, this Sievert's technique is basically here two, uh, like a closed system is there where two chambers are there in which one is hydrogen is placed and then another argon is placed. That is a argon is the reference gas. Okay, so when the valve argon is the reference gas, and here is a specimen chamber where in this pressure change due to volume change, basically a sample is taken, a solid is taken in which we will see if the if the depending on the adsorption and desorption of the sample, the pressure inside this closed chamber or closed system will decrease or increase. That is basically calculated here. So the pressure change due to the volume change and hydrogen adsorption desorption of the sample is measured when the valve between the reference volume and sample cell is opened. So if we open the open both the chambers, open both the valves, that is the reference valve and hydrogen valve, if we open them, then the gases move towards the specimen chamber and the hydrogen gas gets absorbed. If it gets absorbed, then the pressure inside the specimen chamber decreases, and if the pressure gets if the hydrogen gets if the gas gets dissolved, then the pressure inside the chamber increases. So that is basically it is basically displayed as a pressure composition isotherm. Okay, so the detection limit here, it depends on the capability and sensitivity of pressure transducer. Advantage is cost effective and robust and relatively simple, and disadvantage is less sensitive to low density samples and porous material with low storage capacity. So basically, a solid is there. As I told, that storing hydrogen in the form of liquid, as I earlier I told also that storing hydrogen in the liquid form or gaseous form is more dangerous. So storing hydrogen in the solid state is easier. Is safer. So here we have to find various techniques. How do we store hydrogen in solid state? So simplest technique is storing hydrogen in porous materials or porous nanomaterials, so that hydrogen gets adsorbed on the surface or in the pores between the porous nanoparticles. So that is the safest technique. Okay, so characteristic that is used to determine here, there is a technique based on volume or pressure change. Okay, now, gravimetric technique is basically a pressure change is basically in gravimetry, pressure is changed in steps, and hydrogen adsorption can be characterized by measuring the mass change of sample during hydrogenation. A solid sample is taken. Hydrogen is introduced to the sample in steps. Basically, stepwise hydrogen is introduced. Hydrogenation of the sample takes place. So, as the hydrogen of the sample takes place, the change of the mass of the sample takes place. That is basically, it tells us change of the mass takes place, and which is the sign of it change in the mass. We can determine the amount of hydrogen that gets absorbed or adsorbed in the surface of the solid sample. Compared with the Sievert's technique, mass change of sample can be measured directly and continuously. So these are the detection limit depending on the capability and sensitivity of the microbalance. Then these are some of the advantages and disadvantages, and these are the characteristics which are used. Basically, you can measure gas absorption, desorption based on the gravimetric change, and it is suitable for low density samples such as CNTs and MOFs. Okay, coming on to secondary ion mass spectrometry. In this technique, the secondary ion produced by the ion bombardment on a sample surface will be analyzed to reveal the chemical composition and structural information. Basically, uh, basically the a secondary mean if suppose a solid is there in which hydrogen is adsorbed, okay, it is already adsorbed, then another ion beam is bombarded on the sample surface, and due to which secondary ions are released. These secondary ions will be analyzed to reveal the chemical composition and structural information of the sample. Okay, SIMS is very sensitive technique and it can detect most elements up to ppb level, that parts per billion level, also part per billion level elements. It can also analyze that. Okay, I mean it is very sensitive machine. Even up to parts per billion amount of hydrogen or any element is present, then it can detect that also. Okay, so I'm not reading all this because a lot of slides are left. So I'm not reading these advantages and disadvantages. Whatever is necessary, I will read. Okay. So characteristics it determines are acquiring the surface and subsurface information via destructive ion bombardment, and characterization for both bulk and thin film samples are possible. Now, thermal desorption spectroscopy, it is a simple and non-isothermic, physically non-destructive technique to study the surface kinetics of adsorbate by measuring the gas desorption rate in vacuum desired gas environment with controlled temperature ramping. Okay, so what happens here? It is basically simple non-isothermic, non-destructive technique in which surface kinetics of the adsorbate is studied by measuring the gas desorption rate in a vacuum or desired gas. I mean, if you suppose, for example, if you take a sample in which hydrogen is already adsorbed, and you heat it, then obviously it will gas will expand and it will release out of the pores, and the gas that comes out, the rate with which the gas comes out, it can be determined with the thermal desorption spectroscopy. But the thing is, you need to heat it in a, I mean, all this heating, it takes place in a controlled temperature ramping rate and controlled environment. Okay, the characteristics is facilitates gas desorption based on applying thermal gradient. Quantitative analysis is possible if well calibrated standard is provided, and the technique is suitable for sample which remains stable under vacuum process. Neutron scattering, it is very similar to X-ray diffraction, but owing to the intrinsic properties of the neutron, the study of light atom in the lattice becomes possible. So here what happens, suppose here the hydrogen sample is pressured hydrogen, it is inlet, this is the inlet, and this keeps on rotating. So here hydrogen is there, pressured hydrogen, which keeps on rotating, and neutron beams are incident on this sample, and these are the transmitted neutron beams which falls onto a fluorescent screen. And here you can here at the CCD camera you can analyze the you can get the information regarding the structure of the hydrides and hydrogen diffusion dynamics in the most materials. You can see on this CCD camera. Okay. Now, electrochemical characterization. So, this technique focuses on the effect of hydrogen diffusivity in bulk electrode and charge transfer and distribution of electrode electrolyte interface. So, electrochemical analysis can be done using either EIS, that is electrochemical impedance spectroscopy. Then there are various other techniques such as cyclic voltammetry, and all those techniques can be used for the determination of hydrogen diffusivity in bulk electrode. Then charge transfer resistance can be measured uh, using impedance spectroscopy, then distribution at the electrode electrolyte interface, and the hydrogen atoms resulted from water reduction at electrode electrolyte interface will be adsorbed at the surface of the negative electrode, and then they diffuse into the metal to form metal hydride. So basically, all these diffusion coefficient, then charge transfer resistance, all these can be determined using impedance spectroscopy that comes under electrochemical characterization. Okay. So methods used for hydrogen storage. So as I told that hydrogen can be stored in various forms, in liquid form or in gaseous form or in solid state form. But in the case of liquefaction, what is the problem? It requires large expenditure of energy as use of insulation for liquid hydrogen requires low temperature. So as hydrogen is liquid at less than 20 Kelvin. So this insulation required to keep it at liquid state is it is very like expensive. So that liquefaction is also a problem. Then the gaseous in storing hydrogen in gaseous state is also a problem, which is limited by volume consideration because of hydrogen low density. Even at high pressure, very large volumes are required. Mean to even keep it at very high pressure, also very large volume of containers are required. So storing hydrogen in solid state is much better, done by either adsorbing or reacting with metals or chemical. Mean either by absorbing the hydrogen into porous nanomaterials or by reacting them with metals forming hydrides, we can store them in solid state, or chemical compounds or storing in an alternate chemical form. Okay. Solid state hydrogen storage. It is basically done in two ways, that is chemisorption of hydrogen atoms or physiosorption of intact hydrogen atoms. In chemisorption, basically absorption into matter, binding of hydrogen atom occurs onto the surface. So chemisorption is basically adsorption of hydrogen atoms onto the surface of a solid. In case of physiosorption, the hydrogen molecule is bonded on the surface of adsorbent. So here it is bonded on the surface, whereas in the case of chemisorption, mean here it is adsorbed on the surface. Okay, and in the case of chemisorption, it gets absorbed into the pores. Okay, in the case of physiosorption, only at the surface, it sits at the surface. Okay, whereas in the case of chemisorption, it gets absorbed into the pores of the solid. Okay. Liquid state hydrogen storage. Hydrogen can exist in liquid state in extremely low temperature, that is minus 253. So maintaining that minus 253 all the time is a very hectic task. Liquid hydrogen requiring the additional application of compression is stored in cryogenic tanks. So for to store liquid hydrogen, cryogenic tanks are required since very low temperature is required. The cooling and compressing process consume energy, resulting in a net loss of about 30% of the energy that liquid hydrogen is storing. The storage tanks are reinforced and insulated in order to withstand the pressure applied and to preserve temperature levels. Still, research in the field of liquid hydrogen storage is performed, focusing in the development of composite tank materials and improved methods of liquefaction. Okay. Now, gaseous state hydrogen storage. Hydrogen can be compressed into high pressure tanks in a gas form. It also needs extra energy in order to achieve the compression. The space occupied by the compressed gas is large. Even after compression, still a lot of space is required to store this compressed gas, and the compression vessels should be regularly tested to ensure no leaks are taking place. Okay, compressed hydrogen store technology is more cost efficient than the liquid. You mean in the liquid storage is costly, whereas in the case of compressing hydrogen, it is still less costly compared to liquid storage. Okay. Furthermore, it involves less infrastructure and it has been operating in a number of experimental hydrogen filling stations in Europe and USA. Now, coming on to some of the key challenges which are associated with this, the kind of materials mainly used for hydrogen storage includes carbon-based materials, transition metals such as dichalcogenides, magazine, then metal oxide frameworks, that is MOF. All these materials have high specific surface areas but exhibit weak binding forces with hydrogen. They have high specific area, good porous structure, but binding energy with hydrogen is not that good. So that is a challenge. And a great deal of research shows that metal decorations, including alkali earth metals, are effective to increase the binding energy of hydrogen on the sorption based materials. So these metals can be used, but they are not that widely present. Okay, some of them are present, but some of them are not. They mean all these metals also come with different challenges. Hydrogen storage in carbon materials is increased by decoration of these materials with transition metal because of hydrogen spillover phenomena. So there is another phenomena which is a challenge, that is hydrogen spillover. What is hydrogen spillover? It is basically the migration of hydrogen atom from the metal catalyst onto the non-metal support or adsorbate. Spillover, it is a transport of species adsorbed or formed on a surface onto another surface. For example, if there are there is a metal and there is an adsorbate take place, so the hydrogen easily migrate from one surface to other surface. Okay. So hydrogen spillover, it is carried out in three steps. Molecular hydrogen is split via molecular hydrogen, that is H2, gets split into H positive and H positive, 2H positive basically. It gets split via dissociative chemisorption onto the constitutive atoms on a transition metal surface catalyst. Migration of H atom from the metal to the substrate takes place, and diffusion of H atom on the substrate or in the bulk of the material. So hydrogen gets easily transferred from one surface to another, one like metal to or to another metal surface. So that is also a problem. Selection of nanoparticles for hydrogen storage. So selection of nanoparticles, they should have good surface area, then good thermal stability, high porosity, and good mechanical strength. Some of the materials for hydrogen storage, they are the MOF, that is metal oxide framework. These are metal oxide frameworks. They represent a class of synthetic porous materials. So these MOFs, they are highly porous materials. Okay, that stores hydrogen energy at molecular level. MOFs have a very high number of pores, surface area, which allows high hydrogen uptake in a given volume. Various varying several factors such as surface area, pore size, catenation, ligand structure, spillover, and sample purity can result in different amount of hydrogen uptake in MOFs. Now, another type of nanoparticle, that is carbon nanotube. They are microscopic tubes of carbon with 2 nanometers thickness across, and that can store hydrogen in their microscopic pores or within tube structure. Nanotubes have single or multi-walled, I mean they are of two types, single-walled carbon nanotube and multi-walled carbon nanotube. Okay. Multiple absorption sites, high packing density, and possesses an estimated capacity of 6 weight%. CNT and buckyballs have been modified by transition metals, mean we can also modify this CNT to further increase the absorption of the hydrogen onto their surface. Then another is graphene. As I told, graphene is a very versatile nanomaterial. It is used in almost all the fields. So graphene is a 2D honeycomb geometry nanostructure which has porous framework, great chemical stability, and onboard reversibility, rendering a promising hydrogen storage medium. Okay. Hydrogen can store into the interaction between hydrogen and graphene can be tuned by adjusting the distance between the adjacent layers. We can do modification, as I already told. We can do a lot of modification to improve the adsorption properties of these nanoparticles. Okay. Now, fullerene, it is represent a class of novel hollow all carbon structure based on transforming hexagonal carbon motifs via the edge subdivision and modification. So basically, as this carbon nanotube, they are basically like this kind of tube with the benzene rings all joined together. Okay. In the case of fullerene, this is a basically a hollow ball joining by this benzene ring all together. Okay. So this is a sphere, hollow sphere. This is a hollow cylinder, and the surface of them is made by like this, by honeycomb structure. Okay. So these rings are responsible for creating the spherical curvature that leads to the formation of C60 molecule. The fullerene structure, it is a C60 molecule. In case of metal atom supported on carbon fullerene, the large electronegativity of C60 facilitate the transfer of electron from the metal atom to C60, thus leaving the metal atom in the cationic structure. You don't need to memorize all this, just try to memorize the structure, memorize the C60. So basically, try to memorize if there is some geometrical shape written. For example, here it's geometrical shape, it is called truncated isohedron. Okay. Then metal hydrides. Metal hydrides. These materials have the ability to absorb hydrogen and release it later, either at room temperature or through heating of the tanks. They tend to bind strongly with hydrogen, creating a need for high temperature of around 120 to 200 degrees C to release their hydrogen content. Hydrides chosen for storage application provide low reactivity and high hydrogen storage density. So these hydrides, they can easily store hydrogen, and easily it can release hydrogen also by heating of the tank. Okay. Hydrides suffer from severe limitations like skin and eyes irritation as they react violently upon exposure to moisture. So this is a problem with hydrides. These are some of the examples of metal hydrides. Then another is the zeolite, which is a Greek word, comes from zeo, which is to boil, and lithos to stone. So hydrogen are forced to move into the cavities of the molecular sieves under elevated temperature and pressure, which are of different pores. So zeolite, it is a porous structure, and the hydrogen gets stored within these pores. Okay. When zeolites are cooled to room temperature, hydrogen gets trapped inside its cavity, and which can then be made to release by spraying raising the temperature. When at room temperature, hydrogen gets stored, and if you want to release the hydrogen, you can raise the temperature. You can heat the zeolite. They are known for their high thermal stability, low cost, and adjustable composition. Okay, coming on to covalent organic framework. So basically, they are the organic building units which are held by a strong covalent bond, that is CC bond or CO bond or BO bond, that is boron oxide or silicon carbon bond, rather than metal ions, to produce materials with high porosity and low crystal density. So these COFs are also highly porous structure, and this class of sorbent materials, they have been designed to possess pore dimensions comparable to the length scale of molecular diameter of hydrogen. It is easier to tune the pore structure of these COF materials to make them comparable to the molecular diameter of hydrogen, which makes them easy to absorb them. They are lightweight and composed of open channels based on aromatic carbon. The main advantage of 3D COF with respect to other light porous organic material is their crystalline framework, which generates a high surface area. Okay. These are some of the applications and advantages and disadvantages associated with the hydrogen storage. Okay. Now coming on to the thermal energy storage. So basically till now we have studied how to generate energy from the thermal energy. So only generation is not fine. We need to store this so that we can use it at later time. So thermal energy storage systems can store heat or cold. It is not only heat. You can also store cold to be used later under varying conditions. Where cold, for example, if you need to store some medical implant, for example, for implantation, you need to store a organ. Okay, so in that case, you need to store cold also. Okay, the main use of TES is to overcome the mismatch between energy generation and energy use. So basically, it is the main advantage of this thermal energy storage is to use the whole amount of energy, thermal energy generated, to store them to use it completely at a different time, or to not waste it basically. It involves three steps: charge, storage, and discharge. There are different types of thermal energy storage devices, mainly sensible heat storage, then latent heat storage, and then chemical reaction heat storage. So coming on to the sensible heat storage, it is basically the thermal energy is stored based on the specific heat capacity. So here, no change in the phase transformation takes place. So no phase transformation should take place in this case if you are trying to store sensible heat storage. It is basically on the basis of thermal energy is stored based on the surface is based on the specific heat capacity of the material. Okay, the temperature of the material varies and does not undergo any phase transformation during charging or discharging cycle, and this is the formula. The amount of energy stored can be measured using this formula. Okay, so the energy stored, it depends on the amount of the stored material, specific heat of the medium, and difference between the change in temperature. Okay, now coming on to the criteria to choose materials for heat storage. So they should have good high specific heat, long-term stability, it should be non-toxic, unaffected by the contaminants, and it should be inexpensive. So coming on to some of the media in which this sensible heat storage can take place. For example, solid, uh, as here it is of two types, solid and liquid. So coming on to solid and liquid, it is solid. thermal energy storage materials. They are basically such as sand, brick, concrete, rock. They can are used for both low and high temperature applications. So these are the materials. If you heat them, uh, they will not obviously they will not change phases at lower temperatures. So you can use to heat. You can use to store heat energy in these solid materials. The advantage of solid storage materials are low cost, no boiling, freezing, or leaking during operation. However, the disadvantages include microbial activity due to heat and moisture and require high volume for storing thermal energy. But the only problem is you need a large amount of these solid materials to store heat energy. So the thermal properties of various solids storage media depends on various parameters such as size, shape, porosity, and material. Okay. Coming on to the example, they are suppose sand rock minerals, reinforced concrete, then magnesia fire bricks. They can be used for storing heat energy. Now coming on to liquid storage media, in liquid water is the best and most commonly used storage media for low temperature. I mean, obviously you can go not go above 90 or 100 degrees C, otherwise it will change the phase. Then other subsequent materials are petroleum-based materials, that is oil, liquid sodium, molten salts. But the problem with them is that they can release some toxic gases while getting heated. Okay, so the nanomaterials in liquid storage media, to be specific, nanofluid. Nanofluid, it is not like a fluid at nanoscale. It is basically the nanomaterials dispersed in a fluid to improve its heat storage capacity, to improve its heat taking capacity. That is basically a nanofluid, basically a fluid in which nanoparticles are dispersed. It is a class of heat transfer fluid obtained by dispersing nano-sized particles, fibers, or tubes in the conventional base fluid such as water. For example, if you disperse heat-absorbing nanoparticles into water, you disperse them nicely, you make a suspension. So that is basically a heat transfer fluid or a nanofluid. Different nanomaterials such as uh, copper oxide, alumina or CNTs, etc., they can easily get absorbed. They can easily absorb heat energy if you disperse them in liquid. Okay. And coming on to latent heat energy, in latent heat storage, the process of storing and retrieving the thermal energy is based on the latent heat of fusion, where storage medium undergoes a phase transformation. So in case of latent heat, it depends on the latent heat of fusion and phase transfer takes place. So as the source temperature increases, the chemical bonds of the phase change materials break up, and which leads to the transformation from one phase to another. For example, taking water into consideration, if it, I mean, in the solid state it is ice, then if you apply heat, then it changes to liquid, that is water, and if you apply more heat, it gets changes to uh, vapor. Okay, so that is basically a phase change material. So this is the energy stored in latent storage media. It is given by this formula. And the phase transformation of the material can be solid solid or solid liquid or liquid gas. So criteria to choose PCM, that is phase change material, it should have high thermal conductivity, high specific capacity, large latent heat of diffusion, and high thermal cyclic stability and low cost. Okay. And the latent heat storage materials, there are three types basically: organic, inorganic, and eutectic. So, organic, there are two types, that is paraffin, non paraffin. Then, metallic are and salt hydrides in inorganic, and eutectics basically inorganic, inorganic, or organic, organic, or inorganic, organic. Okay. Now coming on to organic phase change materials, a phase change material which contain carbon atoms, it is organic phase change material. For example, paraffins and non-paraffins. Paraffins basically wax materials, or non-paraffins non-wax materials, and organic PCMs are available for a wide range of temperatures, which are stable till at least these organics, they are stable up to 300 degrees C. For example, some example of organic phase change materials, that is wax, hydroquinone, salicylic acid, alpha glucose, acetamide, and nanomaterials which can be used in paraffins, that is carbon nanofibers, then copper oxide, then iron oxide. Okay, these are some of the advantages and disadvantages involved in organic phase change materials. Whereas in the inorganic phase change materials, they consist of salt hydrates, nitrates, or metallics. Inorganic phase change materials, they can be used at a higher temperature up to a range that is 1500 degrees C, and they have a very sharp melting point. Okay, so some of the examples of inorganic phase change materials are sodium nitrate, then sodium chloride, then magnesium bromide, then potassium nitrate. Okay, and these are the advantages and disadvantages involved. Now coming on to the third one, that is the eutectics. Basically, eutectics, it is a mixture of two types. Basically, a mixture of two. It is a mixture of two or more compounds at a particular percentage. So it is not simply a simple mixture like you mix two at any concentration. That won't work. That is not a eutectic. Basically, eutectic phase change materials are a mixture of two or more compound at a particular percentage of composition. The compounds can be of any combination like inorganic, inorganic, or organic, inorganic. These type of phase change materials melt and freeze congruently without any segregation. Mean they when two compounds they are mixed at definite percentage, they act as one. Even if you heat them or if you freeze them or if you melt them, they will not like phase separate. Sometimes they can, that is also a disadvantage, but most of the times, if you form a good eutectic solution, then they won't segregate. Okay, they freeze to an intimate mixture of crystals, leaving less opportunity for compounds to segregate. Similarly, during melting, different compounds melt simultaneously, which also give less probability of compound separation. Molten salts, some examples like for there is this one example, solar thermal plants which depend on solar energy to produce steam or electricity uses molten salts such as heat transfer fluids. These plants use nitrate based melts that operate at temperature below 550 degrees C. So this is a eutectic solution we are talking about. This is an example where a nitrate, sodium nitrate and potassium nitrate with melting point of 307 and 337 degrees C respectively. The mixture of their mixture, 46 mole percent of sodium nitrate and 54% of potassium nitrate, has a eutectic point of 222 degrees C, which exhibit reduced melting point. Nanomaterials also can be added to improve its thermal storage property, that is such as silica, alumina, graphite, nanoparticles, and these are some of the advantages and disadvantages. Now coming on to the last type of heat storage mechanism, that is the chemical reaction. So heat can be stored in chemical reactions as well. Energy can be stored in a chemical reaction which can occur in both forward and reverse direction. Mean, as you might have heard, there are two types of reactions based on the thermal behavior, that is the endothermic reaction or exothermic reaction. So endothermic reaction can be used to form a product. So energy stored in a product can be regained by exothermic reaction under specific conditions. So for example, during charging, if suppose a reaction is taking place in which it is an endothermic reaction. If suppose A and B is reacting and it is an endothermic reaction taking thermal energy to produce C and D. So if you mix C and D together, then it will form A and B producing thermal energy. Okay, so this is basically reversibility. If in case of reversible reactions, if a reaction is exothermic in one direction, endothermic in one direction, it will be exothermic in another direction. This is an example. Solar energy is sufficient to break iron oxide into FeO and O2. When FeO reaches storage tank and comes in contact with water at low temperature, it will revert back to Fe3O4. So here this Fe3O4 taking solar energy, this is thermal energy, solar energy, it breaks into FeO and oxygen, and after, if this FeO it comes in contact with water, it again forms back Fe3O4. Okay, so now researchers are working on numerous type of solar chemical reactors where to store thermal energy, and it has some of it is a like um, not very explored field, so there are various disadvantages also which needs to be worked on. That is, long term reversibility reaction is a problem, then durability is a problem, chemical stability is a problem, and complicated reaction or for chemical reactions. These are some of the applications where um thermal energy storage is like applicable for food packaging, basically for transport of blood and organs, and then industrial waste heat recovery. Okay, now coming on to the assignment questions. So this was all for the course. I mean, today we are done. That whole syllabus is done. So now coming on to some of the assignment questions. The first one is time required to extract the stored energy in an energy storage device is known as. Anyone? Time required to extract the stored energy in an energy storage device is known as. Okay, the answer is power transmission rate. Time required to extract the stored energy. Okay, so that is power transmission rate. So next, which of the following is not a charge storage mechanism in supercapacitors? Okay, the answer is correct. That is photovoltaic charge generation. Okay, since electrochemical double layer supercapacitor EDLC is also, then Faraday redox reaction takes place and intercalation, ion intercalation, deintercalation also takes place. Okay, then which of the following are functions for flywheel? Coming on to flywheels. Basically, spin the rotor to a higher speed to charge the flywheel. Then let me see if someone of you answered. Okay. So this flywheel, basically it reduces power capacity of the electric motor. All these are the functions of flywheel. It reduces the amplitude of speed function, stores and release energy during the work cycle. Basically, as you can see here, let me come to the flywheel. So flywheel, it stores energy in the form of momentum in a rotating wheel. So basically, if the speed of the like rotating wheel is more, then you can generate more energy. Obviously, the electric motor spins the rotor to a high speed to charge the flywheel. Due by rotating the flywheel to a higher velocity, you can charge the flywheel. And during discharge, if the motor, it can act as a generator and it can convert that rotating energy into electricity as well. And the power electronics are used to ensure that output voltage has appropriate voltage and frequency characteristics. So basically, I can understand this was not like very much discussed in detail, so it is fine. So which of the following are functions of flywheel? So basically, reduce amplitude of speed fluctuation, store and release energy during the work cycle, and reduce power capacity of the electric motor. So all these three are the functions of flywheel. So answer is all of these. So which of the following is true about secondary batteries? Anyone? Secondary batteries, they cannot be discharged. Which of the following is true about secondary batteries? So secondary batteries, coming on to this, cannot be recharged. So this is not true. Secondary batteries can be recharged. They have short lifespan. It is also not true for secondary batteries. They have a very large lifespan because they have different number of cycles, hundreds of cycles they can run for. Then reversible electrochemical reactions. It is definitely true. The secondary batteries, they have reversible electrochemical reactions and always cheaper than primary batteries. No, primary batteries are cheaper than secondary batteries. Okay, so the answer is C. The structure of C60 is called as. Just now we studied this fullerene. It was fullerene. Okay, buckyball structure. And the structure, it is basically asking the geometric structure. So geometric structure of fullerene, as I told you just now, it is truncated isohedron. Okay, it is truncated isohedron. The chemical formula of zeolite is. So let us go to the zeolite. Okay, here we have not mentioned the chemical formula. So let me come to it. So basically the chemical formula for zeolite here, it is basically this. This is the chemical formula for zeolite. I guess I may have missed this thing. Okay. A primary battery is such a battery which cannot be recharged, which can be recharged, or which cannot be conditioned by replacing the chemical, or which cannot be reused. So basically, it is in a more technical manner. Any one of you? Mm. Are you guys here? Anyone? None of you is answering? Hello, Arun mein? Okay, let me complete them. Primary battery is such a battery which cannot be recharged. Okay. Basically, a primary battery, it is simply it cannot be recharged. Okay. The steam from the steam generator in a nuclear power plant is best described as. So the steam that is generated in a nuclear power plant, it is very high heat containing steam. So it is superheated steam, which consists superheated steam at a very high temperature, and high pressure steam is generated in a nuclear power plant. Okay. Then in a biomass gasification, particulate matter is removed. We studied this in the previous lectures. The particulate matter, it is removed using cyclones and scrubbers. Okay. Which of them is the synthesis method for graphene, as we studied recently? So basically, thermal exfoliation of graphite oxide. This is also a synthesis technique of graphene. Then heating nano diamond at 1650 in a helium atmosphere. This is also a synthesis technique for graphene. And camphor decomposition over nickel nanoparticles. It is also synthesis technique of graphene. So all of these are the synthesis techniques of graphene. Okay. Okay then. Thank you for your patience, guys. Today has been a long class, and this was the last class as well. Okay, are any one of you present here? So if there is no problem, then okay, I will upload these slides, study material, and okay then. Thank you guys. Thank you everyone. Thank you for your patience. I'm leaving the. I'll disconnect the class then.